Yesterday there was already a question about orbital moments on surfaces, and actually today I really want to talk about spin and orbital moments of individual atoms on surfaces. Now what I want to do is introduce a very simple model and talk less about experimental results. I hope that will work. I realized this morning that maybe that's a little bit risky. Well, why are we interested in small atoms? Basically, data storage devices shrink while getting denser over time. And so from being really, really large, the size of man, they are really small already nowadays. And how far can this actually go? And all of this is done on magnets. So how small can magnets go with this? Now, ultimately, could it be that you could store something on a single magnet? That's basically the motivation behind studying some of the things we're doing. Now, I want to give a little bit more of an introduction on what's important for really small magnets, and then go on and talk about the results of magnetic atoms on thin MgO films. I was hoping that Harald would talk a little bit about it already, so now he ran out of time, and I'm gonna just go fast over it and hope I'll give you a picture. If you have questions, just interrupt and let me know. And then I really want to focus on modeling these magnetic states with a very simple model to figure out the spin and the orbital properties of these atoms on surfaces. All right, so for magnets, one of the important properties is the magnetic moment. And this basically gives the strength of a magnet. And the larger the magnetic moment, the stronger the magnet. And the second important property is the magnetic anisotropy. Basically, you can think of it as an energy barrier between the two orientations of your magnet. The larger that barrier, the larger that anisotropy, the harder it is to flip the magnet back and forth, and thus the more stable the magnet can be. Now, if you go to really small magnets, you run into problems with quantum mechanics because you don't have a continuous barrier to overcome, but rather you have quantized states that will effectively lower your energy barrier, for example, by allowing tunneling between these states or even between the lowest two states and shorten the lifetime. Now, I won't talk about lifetimes. That will be the next talk by Will. He will go into details of lifetimes. Now, on the atomic scale, the magnetic moment consists of spin and orbital moment. And the magnetic anisotropy comes due to anisotropy in the orbital moment, which comes from ligands surrounding the atom on your surface or in a molecule. And also from spin-orbit coupling, which couples the spin and the orbital moment together. In a free atom, there is no preferred axis, so no anisotropy. The spin and the orbital moment can point in any direction they want. And so basically the spherical average, or the average in one direction, is basically zero. You don't have a magnetic moment yet. You have to guide your moment in a certain direction to make it have that. And in other words, if you think of it in terms of d orbitals, that means all your d levels are degenerate. And now, if we talk about here, I want to talk about d orbitals and transition metals. So, for example, for cobalt, you could fill in your electrons according to Hund's rule into the individual shells. For example, for cobalt, that results in a L equals 3 ground state and S equals 3 half, with Hund's rule maximizing L and maximizing the spin. All right, now if you place your atom on a surface, these ligands that are surrounding your atom influence these energy levels. And for example, you could think of it that these
these 2D orbitals won't have the same energy anymore because there is these blue atoms surrounding your atom. And that means your energy levels are split up into different states, which is equivalent to saying your orbital moment is quenched. Now, what happens if you had a situation where some of your orbitals were degenerate? For example, here I drew it where two levels are degenerate and one electron basically is shared between these two levels. You can imagine this in a hand-wavy way, basically by picturing two orbitals and then say, well, if they are degenerate, they build more of a ring that allows the electron to orbit around, and that basically is where your orbital moment comes from. So if you have degenerate levels, you can have orbital moment that remains in your system, even though it can be placed on a surface. So the ligands give your system an anisotropy. They give it an axis on which direction your L points in, but they also influence the size of your magnetic moment by influencing your orbital moment. Now, to the experimental part, we use cobalt and iron atoms on magnesium oxide. Magnesium oxide is basically a film. We use only one monolayer on a silver substrate that forms this checkerboard pattern of alternating oxygen and oxygen and magnesium atoms. And the cobalt and the iron atoms sit on the oxygen binding site, which we know from DFT calculations. And the films that form are really nicely square patterns, basically showing this kind of alternating pattern. Now, the important ligands for this kind of consideration, or for what I want to talk about today, are the 4 magnesium atoms around our magnetic atom, plus the single oxygen atom underneath this atom. So this 4-fold symmetry is really important for what properties are in the atom. And we examine these single atoms with 2 techniques. One is scanning tunneling microscopy, and the other one, XMCD, X-ray magnetic circular dichroism. We do all measurements at very low temperatures and at various magnetic fields and in UHV conditions. Now, the advantage of scanning tunneling microscopy is that we can do it on single atoms, that we can resolve individual energy levels, we can do lifetime measurements, which I won't touch on now, and we could even measure total magnetic moments, as Susanne showed earlier. And then in XMCD, it is an ensemble measurement, but it is element specific, and it can measure spin and orbital properties individually, which Harald showed before. We complement these 2 experimental things with density functional theory, calculations, and multiplet simulations. So to probing the spin state with the STM, we've seen this yesterday already. Basically, use an STM tip and probe your magnetic atom by measuring conductance through that atom. And as long as there is your energy is not high enough to hit an excitation in your atom, you just see constant conductance. Once your bias is large enough that you can actually excite something in your atom, that could be a vibrational excitation or a spin excitation, you open up a second channel, conductance channel, that appears as a step in conductance. So in our case, we are talking about spin excitations. And for cobalt atoms, on MgO, these excitations are actually really large. They are almost 60 millivolts. And for iron, on the same surface, this is now a little bit fast, I hope it's still fine, it's 14 millivolts. which is still, for both atoms, a lot larger than some of the examples that we saw yesterday, where the largest excitation was around 6 millivolts. So, to the XMCD measurements. In XMCD, you use circularly polarized light, shine on a sample, and measure the absorption spectrum. And that absorption spectrum is different depending on the circular polarization of your incident light. What you do is basically you excite from core levels into the valence band. So with either polarization, you can excite one spin polarization or the other one. And the difference between these two absorption spectra is the XMCD spectrum. And in real experiments, or in our experiments, this basically looks like that. Doesn't look as pretty as the ones that Harald showed before, but one of the reasons for that is the spikiness of these peaks is actually an indication that we really measure single atoms. And the second thing I want to point out here is, maybe you noticed in some of Harald's plots, these two peaks were pointing in opposite direction. One was above the line and one below. And having them both basically, in this case being negative, means that we have a large orbital moment on the surface. We can see that directly in the spectra. And again, in a hand wavy picture, you could think of, I said before, a large orbital moment is a half-filled shell. So if you have a half-filled shell, the absorption both times is easier with one polarization of your light versus the other one. The next thing that I would like to point out with these measurements is that if we change the incident beam to grazing incident, the difference is pretty large, and that means there's a large anisotropy in the system. Now, to get more information out of these measurements, one of the things that our collaborators did were multiple calculations, and these basically simulate these spectra. Now, these simulations don't only include of course, not only the absorption into these higher excited states, but they also contain information about the ground states, which again is really important for our single magnetic atoms probed by STM, where we are more close to the ground state in what we're mostly interested in. So some of these simulations of the ground state could look something like this. This is the multiple calculation for the iron atom, and don't worry about it if it's too complicated. I'll guide you through it in a simpler way in just a little bit. But first of all, there's different contributions from the ligands, labeled here as axial and cubic, and they will split the different energy levels depending on how they react to these ligands. And then what you also have to include in such calculations is spin-orbit coupling, and you can include an external magnetic field. So let me show you a very simple model to do something like this, but very simplified. All right, what we need is, we need to know the symmetry of our system, the influence of the surrounding atoms, or what's called the ligand field. We need spin-orbit coupling, and we start with basically the free atom ground state. For iron, this has, for example, in the D6 configuration, this is an L equals 2, S equals 2 ground state. For cobalt, it's L equals 3, S equals 3 half in its D7 configuration. All right. What we use is density functional theory calculations to determine the position of the atoms. So we have these nice calculations from our collaborators that show exactly where the iron atom is with respect to the oxygen and Mg, or the other way around, and the same for cobalt. And the structures are slightly different, as you can see. These DFT calculations can also give us the spin density, which, as you can see, looks quite a bit different between iron and cobalt on this surface. Here it's more with 4 lobes, while for the cobalt it's pretty cylindrically symmetric.
Now, once we know all the positions of the individual atoms, we use a point charge model to calculate the ligand field parameters. And finally, we use Stevens operator equivalence to calculate the ligand field. All right, for iron, the starting point, as I said, is a D6 configuration, which has L equals 2 and S equals 2 in its ground state. So basically, all the states of this lowest part they're 25 degenerate states, and they all consist of different linear combinations of these kind of multi-electron wave functions. And I'll just simply label them as with their ML and MS quantum number now. So first, we want to look at the influence of the axial distortion that's basically due to the oxygen and the Mg atoms. So there's two terms that we have to include here. One, the first one is proportional to Lz squared, and the second one includes also some Lc squared, but mainly Lc to the fourth. And that basically splits our energy levels into 10 degenerate states at the lowest energy levels. Those are ML plus and minus 2 states that were split down. And then we have ML plus minus 1 states that are higher in energy, and ML0 states, even higher up. Now, the next thing that we have to include is basically the cubic part due to the 4 Mg atoms around our atom. So basically, again, I'll recall, even though this is not single electron pictures, the symmetry of the multi-electron orbital is similar, so I can still use this kind of simplified d orbital picture here. Basically, it's the difference between these two is now included when we use this fourfold term, and that one basically splits states here of the lowest two states. It basically splits states with delta ML equals plus minus 4. So the lowest state with ML plus minus 2 are mixed by this kind of term, and we end up with something that's really an equal mixture of the two. Now, before I zoom into that, I will just compare to cobalt on the same surface. Now, cobalt has 1 electron more. It's in a D7 configuration, and that basically means it has L equals 3 and S equals 3/2. And that, in that case, what happens basically as the lowest energy, the lowest state that are split down in energy are the plus minus 3 states. And these cannot be split with that fourfold term of the delta ML equals plus minus 4. So here we still have degenerate states at the bottom, degenerate orbital states. So just to compare the two again, cobalt doesn't have any splitting, and iron does have splitting of the lowest states, which means this splitting is equivalent to quenching of the orbital moment, while here, because it still has degenerate states.
Sorry, can you say that again? Why is it that the cobalt doesn't split?
So basically the term that splits it is L plus to the fourth plus L minus to the fourth. That splits terms that have delta ML plus minus 4 and with 3
Okay, so
plus minus. This one would need a 6-fold symmetry plus minus 6 or a 3-fold symmetry to basically split it.
The term that does the splitting is still there because the symmetry is
Yes,
still
and you can actually see that the higher one, the ML plus minus 2, is split too.
Okay.
It's still there, it just doesn't affect the ground state, which is what we're mostly interested in. Yes?
The same point which you're asking, because I mean, just naively seeing it's S 3/2. Shouldn't be without a magnetic August degeneracy? Kramer's degeneracy?
For the spin, yes.
So far, this is only orbital states.
Right.
All of these are, this is 8-fold degenerate, and here it's each 5-fold degenerate. I'll come to spin-orbit coupling in a second. Was that?
Okay, so
All right. So zoom in onto that. This splitting of the lowest states for iron basically means that we have equal mixtures of ML plus minus 2 states. And both of these are 5-fold degenerate states, while for the cobalt, we have still degenerate orbital states, so 8-fold degenerate lowest energy state. And in terms of LZ expectation value, this means that here, at this point, after including that cubic field, the orbital moment for the iron is fully quenched, but for cobalt, it still remains the full plus minus 3 orbital moment. Now, that is also what you could see before in the DFT calculations, where you have a nice 4-fold symmetry in the iron, but a very almost perfectly cylindrical symmetry for the cobalt. Now, the next thing you need to include is spin-orbit coupling. Spin-orbit coupling basically aligns spin and orbital moments together. And in this case, basically what happens, it splits the different spin states up. Now, for iron, you can see, at least at the beginning, it's more quadratic with this spin-orbit coupling term that the splitting happens, while for the degenerate states of cobalt, the splitting happens basically linearly. And what remains is still a spin doublet that's almost a doublet for iron, and that's really, truly a doublet for cobalt. And these lowest states now don't only have an orbital moment that's important. Yes?
What's responsible for that different behavior?
For the two?
Yeah.
It's basically perturbation theory. Here is second-order perturbation theory because you have split terms. Here it's first-order perturbation theory because you have degenerate levels.
Okay.
And then, yeah. Yeah. Pretty easy. All right. So the splitting that we obtain of this is 13 millieV between the lowest state and the next excited state at 0 magnetic field for iron, and about 55 millieV for cobalt. And I'd like to remind you that the experimental result was 14 millieV for iron and 58 millieV for cobalt. So the results are pretty similar, but keep in mind here, this is slightly larger than experimental value, but I didn't use any fitting parameter. This is only DFT values and all tabulated spin-orbit coupling constants. So no fitting parameter still gives a very good result in this term. And it definitely gives the same order of states, so the same qualitative behavior as the multiplet calculations as a fit to the XMCD results. And as the last thing that we could include is just Zeeman term, which will split the different doublets according to their magnetic moment. So to summarize, if we kind of look at these usually drawn levels, you could say, all right, in this case, for atoms on MgO, they don't only consist of spin, but also of orbital moment. And now here, I corrected it to fit to the experimental value, so we get about 5.2 μb for iron on this surface in the z direction, and for cobalt, we get 5.5 μb when we basically use this full Hamiltonian. So basically what I showed you today is basically a very simple model to basically figure out what the magnetic states are based on DFT determined atom positions and on a point charge model with Stevens operators. And there were lots of people involved in the experimental work. Here is the DFT group at the IBM. Sebastian did the multiple calculations, and then, of course, lots of XMCD with Harald and the group at IBM that was involved in this.